So I hope it's clear now why it is it cool? It's cool, right?
Actually, I don't think I exactly understand the title because why they have those two different lines. I'm not sure I understand.
Okay, let me go back. Did you understand this reasoning over here? That if I start out with 0, 3 and I line up the elements, the coset. These are cosets, by the way, of 0, 3. So if this is the one coset of A equals 1, and this is the coset generated, right? And if I place the cosets in little color-coded boxes, and I make this formulate, this will always happen with a normal subgroup, by the way. I can do this with any normal subgroup.
So wait, so when you take like 0 and 3, you actually multiply them element-wise, right?
You add, it would be addition in this case.
You add them element-wise.
Right, it's your addition that you have off of normal subgroups that I gave you formally at the last lecture.
Okay.
Last lecture I gave you a formal addition of how you put together the cosets, right? You have a actual binary operation acting. The elements of your smaller group are the cosets.
Yeah.
And the binary operations, whatever the binary operation was here, would just slam the cosets together with that binary operation. So you're just taking this coset and binary operating it with that coset, and you get this object here. So if you replace the coset with coset green, coset blue, coset yellow, you get an entirely new subgroup, but with 3 elements where you used to have 6. So now you've modded. It's modular arithmetic on groups, right? It's really cool. Well, that's not opinion, but is it shared? Humor me. But it won't work. If you look at, you should try more examples than what he has here. I don't think, did he try D4? Is that one he tried? Or S4? He D3? S3? Yeah. So he took the second smallest, the next smallest thing you could that was non-abelian, but you could take D4 and try it out. It won't work. Just take some non-abelian and then find inside it a coset, a subgroup that's not normal. And then once you do that, this trick won't work. So you're modding. So we can actually have a formal definition of what we mean by modding. You're modding, that's what you're doing. You're doing the same thing that you did with Z, and then coming back down and making the little packets Z2. You know, you're starting with an infinite set, and then making 2 manageable packets, and then making a group out of it. That by itself is really cool. I think so anyways, when you first see it. But you're doing the same thing here with groups. You're taking entire groups, and you're modding by a subgroup. And so we have a formal definition of what we mean by modulo a subgroup. And that is, we call this a factor group, or it's called a quotient group. And I forget what Frele uses. I think he uses factor groups. So this is the formal definition of G/N. And the objects in that set are cosets. Just like the green, blue, yellow, those objects are cosets. So the elements of this set are going to be cosets. And we have a binary operation on that set of cosets. What do we mean by it? I already gave this to you last time. I'm just trying to put it into context of where it fits into group terminology. So we just binary operate the elements on the coset, which is the question you just asked. It turns out that when n is a normal subgroup, that G/N is a group, and with that binary operation as defined. So it's just that image. You need to have a good example in your mind. I think I told you this already. I got a paper rejected once because I had all these wonderful theorems in it and no examples. And the reviewer said, no, good theorems come from good examples, not the other way around. Don't derive from me an example to fit your theorem. The other way around, please. Tell me why this theorem is important by giving me a good example. So I hope I gave you a good example back then to tell you why this theorem is really cool.
Is there ever a time that operation would be different than the operation you're using with G?
No, it has to be induced from the original G.
I figured as much.
Yeah, it's just like, to me, I think of Z and Zn. The Zn is taking the addition, but they're modding out by something, right? So you are in somewhere there's gonna be some kind of rotation around, right? Like you do with Zn. So I just wanted to give you a visual. These are the cosets, h, 1 plus h, and 2 plus h. I was talking about them up in the air. Those are the cosets that are here. These are the actual addition of these cosets. These are the actual binary operatings of these cosets. You actually see it now. So I just showed you the calculation that blue star yellow is equal to green. I didn't realize, but that actually is true, right? Primary colors. That was an accident. So I just gave you an example of a normal subgroup in S3, and I just wanted you to try it out. Try it out. Make the Cayley table for G/n with n is equal to that normal subgroup that we just did. Run through it. Should be fairly easy. Cool, isn't it? If you think this is cool, you're in the right field. Because I think if we gave this same lecture to an engineering department, they wouldn't find it cool at all. And if there was someone in the crowd that did think it was cool, they are in the wrong field. They belong over here. No, 1 goes to 2, 2 goes to 3, 3 goes to 1.
Oh, okay.
Nice. My own abstract algebra background is horrid. So I took a math ed version of an abstract algebra at a sophomore level, and then I never took an abstract algebra course again in my life. The next time I did abstract algebra was John Stevens here at Montclair, and he taught me out of this book. I'll bring it to class. They were using Hebrew letters in the entire book. So when I look at permutations, which are supposed to be simple examples, I really struggle to see them. So I do the 1, 2, 3 at the top like I did before.
Right.
This thing, back. Right here. See how I write it like this? So I can see the 1 goes to 2, 2 goes to 3, 3. I write it out like that. And I think that if I had more familiarity with an example like that, then I would not have to do that. I'd be able to work with the transpositions much better. But that's why I suggested that you at least do this if you're not as familiar with permutations. And so I'd like you also to try, here's another homework problem, try it out when it's not normal and see it scattering all over the place. Actually visualize it, because when you do it yourself, you'll actually see that it doesn't work. And you get a better feeling for it. So explain what happens. And these computations shouldn't be bad at all, because it's just you only have a 3 by 3 here, and the other one you have a 2 by 2. You guys should be rested, right, from last week? I again want to refer you to the math Dr. Bob. It's a YouTube channel, and he has really nice explanation with lots of details. I like the details, and he's careful. He goes through every little piece very carefully. But how can we tell if two sets are the same? We already have the definition of isomorphism because, strangely enough, Fraley gave it even before he defined groups. It's at the very beginning of your book, before groups, which is strange because we talk about group isomorphisms. But if we have a one-to-one onto map just from two arbitrary sets, if you ever take combinatorics, that's a wonderful class to take. But when you talk about two sets being connected in some way when you're counting, you just look for a one-to-one and onto function. And right away you can say that if I have a one-to-one and onto map from one set to the other, they have to have the same number of elements. And in fact, a lot of things in combinatorics are proved in the first few weeks by just finding that one-to-one and onto that injective map. That tells you there's a code book from the map using the map from the first set to the second set. So I gave you some crazy example here. I don't know why it was in my head, but you sometimes have to prove things in real analysis class that, for example, the binary expansion, the binary numbers, they actually equal the reals and are uncountable. Well, if I already know the reals are uncountable and I can find a one-to-one and onto map that maps from one to the other, I can tell you that the binary expansions are also going to be uncountable. So I just showed you this. You probably have seen it before in real analysis, right at the beginning of the semester when they talk about uncountable and countable. If you let the map be the coefficients of base 2 expansion, you'll get this is a one-to-one and onto map. You can change from base 10 to base 2, and both are uncountably infinite automatically. If you know one is, so is the other. In fact, I'll give you a real analysis. If you like real analysis, I'll give you one. I'll give you one where you have to use the binary expansion to prove something else is uncountable. I'll give you one to think about. So with a group, you also want more than that. You want to know more than whether there's just the same number of elements. In fact, in Fraley, he does a very good job looking at Z2 cross Z2 and comparing that to Z4. They're not isomorphic, actually. So you would like to also preserve the binary operation. So what that means is that's called an isomorphism. If you have a one-to-one onto map and it also preserves the binary operation, that's called a group isomorphism. But what about this thing up here? You're taking the big group and going to a small group. So there's no way that you're going to get an injection here because the two groups have to have the same number, right? So you don't get that. But if you have a map that goes from one group to another group, and all it does is preserve the binary operation, that's called a homomorphism, not an isomorphism. So that picture up here is an example of why homomorphisms are important. And I bring this up because I remember learning this in that baby abstract algebra course and not getting it. To me, it was like the teacher was telling me that I have to memorize 2 definitions. Why? Well, that's why. That picture up there is why. Because you want to preserve the binary operation, but you might not have injection. One-to-one and onto. We only have onto, but you won't have one-to-one. It turns out that if you start with a big group and you go to the factor group, G/n, and you define, quite naturally, phi of G to be G times n. So inputs are elements from the group, outputs are entire cosets. It turns out that that's a homomorphism. And that's easy to prove, just by definition. So for example, if I take 2 arbitrary elements from the domain, and I star them, well, by definition of phi, that's G1 star G2 with the n outside. But by definition of what you mean by binary operation on the cosets, that's this thing right here. And that's phi of G1 star phi of G2. So you preserve the binary operation. But it's not one-to-one because you're going from a big fat group to a much smaller group. So it cannot be one-to-one. Is that clear? So that's the picture that you're seeing there. They're doing a mapping. So if n is normal,
should that be read? Phi G to G/n, the normal subgroup?
where
The function from G to the normal subgroup.
we call this a factor group. Factor group. This is called a factor group.
Which is composed of the normal.
It's that definition I gave you on the previous page, right? They don't want to say G/n every time, so they call it a factor group. And they denote it this way. It should make sense why they denote it this way, because you're modding by that particular subgroup. So really, when you're looking at Z2, you're dividing things from Z by 2, right? So you could, in fact, in Fraley, he does take Z slash 2Z. He has nice examples in the book. Okay, well, if you have a normal subgroup, you get a natural homomorphism. It seems to make sense what I just did. Should make absolute sense what I did. But what if you have a homomorphism? Can I get a normal subgroup out of it? Can I go backwards? And the answer is yes. If I have two groups and I have a homomorphism between G1 and G2, it turns out, do you remember this word? Don't say it with such venom. Kernel. The kernel of phi, which is exactly what you remember as the null space from Dr. Song's class. Those are the y values that were equal to 0, but in this case the 0 is the identity element in G2. So if you look at the x values that make the y values equal to 0, which you probably call the null space or kernel in null space in undergrad for sure, and then you probably called it the kernel at some time in Dr. Song's class. If I have the kernel, it's a normal subgroup, and it's not hard to prove. You can prove it. It's all over the place. Should be standard proof anywhere on the internet. Probably is in your book. Okay, questions? I told you that section 13 and 14 are connected to each other. Okay, one induces a homomorphism. The homomorphism induces a normal subgroup. And I think this might be in your book too. I'm sure it is. The fundamental any fundamental theorem has to be covered. It's fundamental. Bless you. So if I have a group homomorphism, then what I know is that the range of phi turns out to be a group. If I go from the factor group of G1 to n to phi of G1, given by this map over here, where n is given to be the kernel, I get an isomorphism out of it. Sometimes I'd like to have an isomorphism. So part 2 here gives you some sets that are homomorphism. And 3, if I have a gamma, which is a homomorphism defined by the natural homomorphism that we already defined, then phi of G, which is this psi up here, composed with this gamma, they're equal. So it's a way, they call this a fundamental theorem because it's a way of proving things where you can connect all the different moving parts with each other. You have the natural homomorphism, you have the homomorphism that ties together the factor group and the range of the this phi, the group homomorphism. You have a connection to the kernel. So this connects all these pieces together. So this is a harder one to start integrating, but I hope that you can see that it's an important theorem because it connects all the pieces that we just tied together.
Can you go back for another 30 seconds?
Sure. Without one,
without the one-to-one?
and onto.
And onto.
Yeah.
What is the same thing?
Just group. It only preserves the group binary operation. So it's on the previous slide, I think, or previous couple slides, and it's also in your book. It also should have its own wiki page, Wikipedia page. I wanted to give you a flavor of some true-false questions. I didn't have any in-class assignment prepared for today. I just think we've been doing a lot. Did that work out well, by the way, doing a homework that was, you could work in groups, and seemed like that worked really well. So maybe we'll do that a little bit more often because I think that it worked well. I have a suggestion box outside my office. You can put a note in there if you don't think something's going well and I think it's fabulous, so that you can let me know, by the way, your idea is not fabulous. I don't like it. So you just let me know if that wasn't something that worked well. Or anything else. Some true or false questions. You don't have to answer them now. I just wanted to give you some of them. Here's one example. If I have a normal subgroup, then is it true that GA equals AG for all G and G and A and H? Play around and figure it out. Suppose I have a subgroup of the direct product where G is a group. So now what will the subgroup look like? Because it's a subset, what does that have to look like? It has to be an ordered pair, so keep that in mind. Are these true? If I know that the G is abelian, do I know that the subgroup of G cross G is abelian? If I know that G is abelian, is it true that H is normal? If I know that H is normal, does that prove that G is abelian? Some things to think about. Here's another true-false question. What about this? If I start out with a group G, and I have a normal subgroup, and the original group G is not abelian, is it true that the factor group is not abelian as well? Can this happen? Number 4. If I have a finite group and G2 is an infinite group, does that force phi to be a trivial homomorphism? Boy, there's no more slides. You know, this is the most fun I've ever had teaching abstract algebra. I've never had so much fun because you guys are feeding me so many questions that I end up walking around thinking, I wonder if this is true. I wonder if that is true. So hence, some musings. Puzzles.